Right, so I think I've been given a very broad mandate, actually, talking to you about AI-powered pseudoCT image synthesis from magnetic resonance imaging. And I feel that this is a sufficiently broad topic. I can probably talk about this the whole day. So this is probably going to be one of these talks where we sort of have sections, we go a little into detail, and other sections we sort of skip over, so just hope to allow some time for questions if anything is missing from anybody's expectations. So let's get started here. So we have the obligation actually in our institution to disclose any financial interests, and they have nothing to disclose here. But just wanted to acknowledge actually this European project called Provision. It's kind of instrumentation related thing. So the aim is to design a PET scanner dedicated for our high resolution, temporal and spatial resolution PET scanner dedicated for prostate cancer imaging. And this is a collaboration with the spin-off from CERN called Provision. And so you can see the device actually which is being tested in our facility. And this is one of the physicists actually operating the scanner. And some of the work that I'm going to present today is linked to this project and obviously funded by this project. So why do we need actually synthetic CT? So the first is that there are a number of scenarios actually in clinical setting which require to avoid actually doing an MRI scan, doing a CT scan in addition to an MR, just quickly through this. So the MR or PET-MR only treatment planning is a typical application. And the idea is to take advantage of the high soft tissue contrast provided by magnetic resonance imaging. There is no exposure, as you know, compared to CT, which is especially important, especially for the pediatric population. And then it eliminates also all the hurdles or the problems that we face with non-rigid alignments or registration between MRI and X-ray CT. Number of issues, actually financial issues like to the cost workflow, it gets much simplified, and especially important for adaptive radiotherapy, where based on combining CT or magnetic resonance imaging, where we don't have access directly to CT, and the CT provides the electron density which is needed for radiation dose calculation, for instance. A concept actually that I learned from the literature called simulation emitted radiation therapy, because merci. I come from the nuclear medicine field, and this is something that we got used to actually in the collaboration that we have with the radiation oncology department, and something which is obviously closer to my heart is PET-MRI. And again, so we need to generate kind of attenuation map that we can use for attenuation correction purposes. So this is the problem, can be summarized actually in this slide here, where you see the X-ray CT, which can be used actually to derive what we call an attenuation map in terms of linear attenuation coefficients at 511 kV. And it's much problematic actually when we use the MR intensities, because there is no direct correlation between the MR intensities, which are obviously correlated with T1, T2 relaxation times and proton density, and there is no direct link actually between the MRI and the CT Hounsfield units or the electron density. And the problem gets more and more complicated for PET-MRI because we usually ignore bony structures. I'm going to show you some examples. The MRI hardware shows it's very difficult to take this into account, truncation issues, susceptibility, and a number of other problems like motion and so on. So why the generation of synthetic CT, so especially when used deep learning-based techniques, can be used for three main applications. I'm going to focus on two, the first and the last one, and try to just mention the second application. So the first is to replace CT and MRI-based treatment planning. Again, PET-MR or treatment planning is the same kind of thing. Then derive the attenuation maps, as I mentioned, for the correction of PET-MRI. So that this is the typical workflow actually that we face for CT plus MR. So we acquire CT, we acquire the MR, and then we face this major problem which requires the co-registration between the MRI and the CT. And then we proceed to the delineation of the regions of interest, the volume, treatment volumes, and also the organs of interest, and then we proceed to the dose calculation. So one of the problems that we face during the registration process is that with the temporal variability between the CT and MRI acquisition, which usually doesn't take place actually during the same day. You see here a couple of examples here. Even if we can easily delineate the, I think you see the mouse here. No, you don't see the mouse for some reason anyway. So you can easily delineate actually the rectum and the bladder on the CT, which is good, but it's very difficult to keep consistent actually the bladder and the rectum filling. And the same takes place also for the GI tracts, where you have the stomach and the bowel. And again, it's very difficult to keep any consistent the filling of the stomach and the bowel because of the temporal variability owing to the fact that the two scans are not acquired during the same day. So the MDs are usually not very happy with these inconsistencies, and one of the solutions to this problem is to move from MR plus CT to MRI-only radiation therapy treatment planning, as you see in this scheme here. And obviously, so the major problem that I'm going to address today very quickly is how to synthesize a pseudo-CT image from the acquired MRI scan. Right, so the pros of moving from CT plus MR to MR-only radiotherapy is summarized here. So basically, as I mentioned in the beginning, you reduce the uncertainty due to misregistration. You deal very well actually with the workflow. You reduce the operational costs. You make it much, much easier actually for the staff and also for the patients. You reduce the radiation dose again, as I mentioned, and this is very helpful as well for MR-Linac guided radiation therapy, and I just took those illustrations here from the recent reports published by the ICRU focusing on the dosimetry for MR-Linacs. You see there are at least 3 vendors providing these MR-Linacs. So the first one is the Elekta, and then you have also the ViewRay. For the advent of PET MRI, so we're interested to do this for the brain. So we first align the PET with the patient's bed, and this is the MR-based technique, and you see that it matches actually very nicely the transmission-based technique. More recently, so some of the manufacturers actually focused on developing special MR sequences which depict the bony structures, because in the conventional T1, T2 weighted sequences, there is kind of ambiguity between air and bony structures. It's very difficult to distinguish them. And those ultra-short echo and zero-time echo sequences enable you to nicely depict the bony structures. So you can easily actually synthesize a pseudo-CT image from the acquired MR. And this is a nice illustration from this recent review paper. We see some different industrial solutions, I would say, so mostly from GE. And you see that basically for the same patients, this is the X-ray CT, and the attenuation maps generated from the zero-time echo, the ultra-short echo, and also the Dixon sequence. So very nice actually work, which is now being integrated into the clinical setting, right? So the Atlas-based technique is a more powerful technique, and I had one of my PhD students actually spent a lot of work developing different algorithms belonging to this class, and this is basically how the algorithm operates. So we've got a bunch of co-registered CT and MR atlases, and then you start with the incoming MRI from the patients, and you decomplex the formable registration with the atlas, so it takes a lot of time, obviously, and then you do kind of regression analysis to synthesize the patient-specific pseudo-CT. The other category is what we call MLLA, or maximum likelihood reconstruction of attenuation activity maps. So this is a very complex process that takes advantage of the high temporal resolution that we have on the commercial PET scanners, and provides actually a solution which unfortunately is not unique in the sense that you have a scaling factor which is difficult to implement, and the generated attenuation maps using this kind of technique are very noisy, as you can see. So this is the conventional MLLA. You see it's very noisy and suffers actually from crosstalk between attenuation and activity maps. And then we did some developments as well to develop kind of a priori knowledge that can be incorporated and forced in the form of penalty functions, so quadratic penalty functions, to improve the performance of the MLA estimates. And you see that the produced attenuation maps are less noisy. Another technique which has been used actually in clinical setting in the context of MRI-guided treatment planning is the direct conversion or classification, like this one actually proposed by Cohen. Again, so it relies on multiple well-aligned pairs of CT and MRI scans, and the only difference is the way to do the conversion, right? So there are multiple statistical based techniques, regression, also some techniques that use multiple MR sequences, and this technique actually is used actually for kind of polynomial conversion based technique, and it really does a very good job in this respect. So deep learning techniques have emerged more recently, and you see how realistic actually the pseudoCT image can be generated from the MR without this intermediate step, which CT. You see nicely here the nasal cavities and the skull, which is extremely well predicted by the deep learning model. So we did some work actually in a few years ago actually with the radiation ecology to generate attenuation, to generate actually pseudo-CT images using the atlas-based techniques that I mentioned previously. And this paper actually published by Electa in 2017 triggered our attention, so we decided actually to go for comparative analysis of the bunch of techniques reported in the literature compared to the deep learning based model. And you see that we're not surprised by the conclusion, in the sense that the deep learning model actually outperformed all the conventional atlas-based techniques. Actually, going through the recent literature, there are a couple of review papers. The first focus on MRI-guided radiation oncology, and the second in MR-guided attenuation correction for PET MRI. You see that the increasing number of papers reported in the literature covering different anatomical structures for radiation therapy, and you see an exponential increase in number of deep learning models that have been published recently. So the model actually is, you've got obviously the supervised and unsupervised way of training the model. In the supervised model, so you've got a bunch of well-aligned MRI and CT images that can be trained actually using a well-defined model. And then you've got the second step, which is the prediction step, where we kind of predicts actually pseudo-CT from the MRI without using actually the patient's CT image. And one of my PhD students developed actually the model that you see here. So there are two major components. We focus on the brain because it's more simple compared to the thorax and the other regions in the body. One compartment actually does the segmentation, and the second actually takes into account the synthesis. It's a very complex model. I'm not going to discuss it because just for the sake of time. And you see basically here some of the results for one of the patients, well aligned with MRI and CT. And this is the pseudo-CT generated by the deep learning model. Compared to the commercial solution, you see major improvements, and this is also reflected in the bias maps which are generated. You see that the commercial solution is really very good approximation. Right, we can also use the same techniques not in the image domain but in the projection domain, and in this work we basically use the sinograms, both time of flight and non-time of flight, to train the network to predict directly what we call the attenuation correction factors in the projection domain. And these are actually the pseudo-CT images. You see that we depict the skulls, the nasal cavities. It's not perfect, but it really does a good job in this respect. And these are the images, the best images, corrected using the conventional approach versus the more sophisticated one that I presented here. Again, for the sake of time, let's go very quickly, actually. I would like really to keep it in 15 minutes. There are some commercial solutions. I'm not going to mention all of them, but we are involved in European projects with this company called Spectronic. They use actually also deep learning model using transfer function estimation algorithm, which does really a good job. You see some examples here. There is some debates in the literature which is the best metric to use actually to assess this pseudo-CT generation techniques. So obviously some metrics are specific to the radiation ecology people, others specific for the nuclear medicine people. We're hoping actually to get kind of agreements during the next few years on this. Now, in terms of bias maps, so if you look to the bias maps, so the error that can be committed in clinical setting when using CT-based attenuation correction versus MRI-based attenuation correction when using commercial solutions, so the bias can be very large, so between 20 and 30%, as you can see in this case. Now, in the radiation oncology field, we're talking about different energy ranges, right? And the differences can be very small in this context. You see the different pseudoCT images that can be generated using the different techniques. This is the water equivalent approach, which is used in clinical setting in a number of institutions that I know. So for the KV that we have in position emission tomography, but if you zoom on those volume histograms, you see some differences here which are well documented. So the other application is obviously to generate the digitally reconstructed radiographs, which are used actually for patient setup and optimization, and can be nicely generated also from the pseudoCT images. So it really does a good job in this sense, and have that within this 15 minutes, I convinced you actually of the role of deep learning to synthesize pseudo-CT images. Just to summarize very quickly, again, for the sake of time, so we can skip some of those conclusions. I think I convinced you that synthetic CT image generation is really crucial in situations where CT is not available, either radiation oncology or nuclear medicine applications. And the key component, the key issue here is the acquisition time for MRI, which tends to be very lengthy. And have one of my PhD students spend 6 months in Stanford University in California, working on this neuromix sequence. It's really multi-contrast sequence involving T1, T2, DWE, and so on. It takes only 2 minutes, but the images are extremely noisy, and he did some work actually to improve the performance, actually, especially the quality of the images. You see here the neuromix conventional sequence, which is obviously takes factor of 20 acquisition time compared to the neuromix protocol. And this is the deep learning model and the bias maps here, and obviously much improve the quality. And this is especially important in cases where you have patient motion. If you have a sequence that takes only 2 minutes, so you reduce significantly the motion of the patient, and also does a good job for handling susceptibility artifacts. And I think the future of MRI is definitely going to go in this direction. Right, so with this, I thank you very much for your attention, and I thank also the funding bodies actually funding our research and my team here, and especially Hussein and Isaac, who did some of the work that I presented here. And also twink to those who graduated this year, so Isaac, Amir, and Azada. So they done actually very good work, and they presented their thesis during this year. Thank you, and then I advertise also for this conference that will take place in Geneva next year. Hope to see some of you there, and I thank you again for your attention.